My name's Robert White, and I just want to explain to you two theorems. One is called the floating plastic theorem, and the other one's called the ocean garbage theorem. They're both theorems about networks of points and lines. But before we start, I just want to explain a few particular elements. The networks are composed of points, edges and regions. Points, 0 dimensions, can be either an isolated point or it can occur at the end of a line segment, or it can occur where two line segments cross. An edge, a short line, we call them edges. These are one-dimensional, and an edge is always joining two points together, or it joins one single point round to itself. So both of those are edges. And then the third element is a region. A region is simply an area which is bounded by a number of edges. So here is a network of points, for example, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 points. P equals 9. You've only got one region, R is equal to 1, and edges, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9 edges, if I've counted them right. That's what we're talking about. And the first theorem is concerning what we call open network, a network with no regions in it. So the first theorem is for an open network, for example, something like that, which has no closed regions, and it is simply P equals E plus 1. Now, supposing you've got a network for which P is equal to E plus 1. Here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. P is equal to 10, if I've counted correctly. E is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So for that network, P is equal to E plus 1. 10 is equal to 9 plus 1. Now what I propose is that if we try and grow that network into a bigger network and keep it an open network, remember these are for open networks, networks with no closed regions. The only way I can grow this network to add something to it is to add a point onto one of the edges, in which case the number of points goes up by 1, but the number of edges also goes up by 1. So you add 1 to both sides of the equation. If the equation worked before, it will work after you've added a point. The only other way in which you can add an edge or a point to this network is to add an edge which has got to terminate in a point. If you add an edge with its terminating point, you've added 1 to E and 1 to P. So the equation will still hold. So therefore, if you have a network for which this is true, it will be true for any network which you can grow by adding points and edges to it. The simplest network you can start from is a single point. Every network can be grown from a single point by adding edges and points to it. This network obeys this rule because P is equal to 1, there are no edges, plus 1, it works for that simplest network, and therefore, because of this theorem, this is true for all open networks which have no closed regions. That's the first theorem. The second theorem that follows on from this is the Squiggles Theorem. There's an explanation of the Squiggles Theorem in volume 1 of Bui's math book. The Squiggles Theorem is points plus regions equals edges plus 1. Here is a squiggle. Okay, 1, 2, 3, 4, 5, 6 points. P is equal to 6. Regions, I've got 2 regions. And edges, 1, 2, 3, 4, 5, 6, 7, plus 1. Edges plus 1. P plus R equals E plus 1. So that theorem works for this particular network. If I want to add a point to this network, if I want to grow it into a larger network, I will add a point onto an edge, or I can add a point to the end of an edge, as we did in the first theorem. If we just add a point or an edge to this network, we know that P will increase by 1, E will increase by 1, and the equation will still hold. The only other way in which we can grow this network into something larger is to join 2 points together. If you join 2 points of this network together, you will add an edge, but you will also add a region. So you'll add 1 to E and 1 to R, and therefore, if the equation worked before, it will still work after you've added that region. The only other way in which you can add a region to this network is to join a point to itself. If you do this, the value of R goes up by 1, and the value of E also goes up by 1, so the equation still holds. So if it works for a simple network, it will work for any other network that you can grow. Start from the simplest network, a single point, 1 point, no regions, no edges, 1 equals 1, it works for a single point. Therefore, it follows that the Squiggles Theorem works for any network. Now, the next theorem after the Squiggles Theorem is the floating plastic theorem. Suppose you've got some bits of plastic floating in the ocean. Okay, 1, 2, 3, 4, 5 bits of plastic. For each one of these networks, we know that the Squiggles Theorem will work. So if I take this first one, let's put down P plus R equals E plus 1, that's the Squiggles Theorem. For this first network, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 points, 1 region, edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus 1. Squiggles Theorem works. For the second network, 1, 2, 3 points, 1 region, number of edges 1, 2, 3 edges, plus 1. 3 plus 1, 3 plus 1. Third network, 2 points, no regions, 1 edge, plus 1. It works. For that 1, 2, 3, the fourth one, this one, 1, 2, 3, 4, 5 points, no regions, 4 edges, plus 1. And for that one, 1 point, no regions, no edges, plus 1. So we know that the Squiggles theorem will work for all these separate pieces of plastic floating in the ocean. If you total up all of these columns, you'll get an equation which still balances. 12, 15, 20, 23. That's the total P. Total regions is just 2. 12, 15, 20. And 1, 2, 3, 4, 5. Plus number of pieces of plastic, which is 5. So that is the floating plastic theorem. For all pieces of plastic floating in the ocean, the number of points you count plus the number of regions you've got is equal to the number of edges you can count plus the number of pieces of plastic you've got. Okay, the next theorem I want to talk about is Euler's theorem. It concerns solid figures and it says that the number of faces in a plane-sided solid figure plus the number of vertices, number of corners, is equal to the number of edges plus 2. So for this cube, I've got 1, 2, 3, 4, 5, 6 faces. 6 faces plus vertices, 1, 2, 3, 4, 5, 7, 8 corners. Number of edges, 4 round the bottom, 4 vertical ones, 4 round the top, 3, 4 is 12. So 12 edges plus 2. That's Euler's theorem. Now, there's a very simple way of proving this using the Squiggles theorem. All you've got to do, let's take this as an example. Suppose you imagine that this box is made of rubber and you can spread out the base and squash it flat. Then you'll get, I'll call this proof 1. You'll get a shape something like this. You see, the top of the box is this bit here. The 4 sides have been splayed out and it's standing on the bottom. So the bottom is that larger square. Now, once you've squashed your box flat, you've got a squiggle and you can apply the Squiggles theorem. The Squiggles theorem applied to this says P plus R equals E plus 1. That's the Squiggles theorem. How many points have we got? Well, the number of points is exactly the same as the number of vertices on the box. So P is the same as V. What about the number of regions? The number of regions here is 1 less than the number of faces on the box because it's standing on 1 face. You've lost a face. So the number of regions here is actually faces minus 1. The number of edges on the box is the same as the number of edges in the squiggle. So that is equal to E plus 1. Rearrange this, F plus V equals E. Minus 1 goes over the other side, becomes plus 1, E plus 2. So that's a proof of Euler's theorem for solid shapes. Any solid shape bounded by plane faces, F plus V equals E plus 2. For example, if you do a pyramid standing on a triangle, faces 1, 2, 3, 4, 4 faces, vertices 1, 2, 3, 4 vertices, edges 1, 2, 3, 4, 5, 6, 6 plus 2. So that's Euler's theorem. There's another proof that we can use for Euler's theorem, but to do that we need to go from your plain squiggles into three-dimensional squiggles. So see what happens if I do a squiggle on a balloon. Okay, I've drawn a squiggle on a balloon. Okay, we know the Squiggles theorem. P plus R equals E plus 1. But on a balloon, we've got a face at the back as well. So we've got an extra face on the balloon. So for a balloon, this is the ordinary squiggle, flat squiggle. On the balloon, we've got P plus, how many regions? We've got one more region there. P plus R equals E plus, we've got an extra region, the back face. So it's not E plus 1, it's E plus 2. So for squiggles on a balloon, we know that P plus R equals E plus 2 because we've got an extra face. Suppose I want to demonstrate Euler's theorem for that cube. All I need to do is draw the cube on the balloon. There's the cube on the balloon, and blow it up. The faces have turned into regions on the balloon, and we've got the balloon version of the Squiggles theorem. Points is vertices. These regions are the faces, E plus 2, which is Euler's theorem again. In other words, you can prove Euler's theorem, F plus V equals E plus 2, by thinking that your solid shape is made of rubber, blow it up like a balloon, and we know that squiggles on a balloon gives you a 2 over there. Okay? So that's another way of proving Euler's theorem. Next thing is all about going from 2 dimensions into 3 dimensions. You remember when we did the very first theorem, P equals E plus 1, we talked about what happens if you add a point onto one of these edges. The number of points went up by 1, the number of edges went up by 1. And we used this idea to prove the very first theorem, F, P equals E plus 1. For the Squiggles theorem, we had to think about joining 2 points together to make an edge, increasing and adding an edge to the Squiggles theorem, added a region, because it's connected. When you draw a line, you get an extra region. Regions went up plus 1. So if you think of the dimensions, the 0 and 1 dimension parts go up by 1. In the Squiggles theorem, the 1 and the 2 dimension parts went up by 1. In the balloon theorem, we're in 3 dimensions, so we've got another element to think of. In this one, the number of regions went up by 1. Remember, we added 1 region because of the back of the balloon. What extra dimension did we get? We get a volume. It's the volume, which I'm calling D, goes up by 1. So the Squiggles theorem on a balloon is not really perfect. How it's not P plus R equals E plus 2 for a balloon. It is P plus R equals E, edges, plus dimension. I call them D. Three-dimensional bit, plus 1. So it's just like the Squiggles theorem. P plus R equals E plus 1. P plus R equals E. If you're in 3 dimensions, count these, plus 1. Then you look at the balloon. Number of points on the balloon, P. Number of regions on the balloon, R. Number of edges, just the same. Number of dimensions in the balloon example, we've got 1 dimension, 1 volume to add to it. So that 1 volume plus that 1 is what gave you the 2 in Euler's theorem. Okay, once we've got this far, we're almost at the floating plastic stage. Now, let's think about the sorts of things you can find. Things like this. Points, P, plus regions, R, equals edges, plus dimension pieces, plus 1. Number of points here, 2 4s are 8. Number of regions for the box was 6. Number of edges, 4 plus 4 plus 4, that was 12. 1 three-dimensional part, 1 plus 1. 8 plus 6, 12, 1, 1. The ocean garbage theorem uses the three-dimensional Squiggles theorem, and we do the same as we did for the floating plastic. So let's have some examples. I'll have a table tennis ball. Whatever it is. 1, 2, 3, 4, 5. And P plus R equals E plus D plus 1. Points for the cube is 8. Regions for the cube is 6. Edges for the cube, 12. 1 volume plus 1. For this thing, point 8, regions 0, edges 7, plus no dimensions plus 1. For the table tennis ball, points 1, regions 1 surface equals no edges, 1 volume, 1 dimension volume plus 1. For this one, 2 points, no regions, 1 edge, no dimensions plus 1. And for this thing, 4 points, 1, 2, 3, 4 regions, 6 edges, 1 volume plus 1. That is using the three-dimensional Squiggles theorem for each of these bits of floating garbage. If you total up these, 16, 23, total R is 11, total for edges 19, 20, 26, number of dimensions plus 1, 2, 3, 4, 5. What have we got here? We've got, for garbage in the ocean, points plus regions equals edges plus three-dimensional volume plus number of pieces of garbage. And that's the ocean garbage theorem. 30 years ago, the North Pacific garbage was discovered, and it's been growing bigger ever since. When I looked up on the web to find out how big this patch was, I was astounded to find out that it was 270,000 square miles. That means if you take the square root of that, you get about 500. That means the North Pacific garbage patch is 500 miles wide. It's mainly composed of plastic. That's not the only one. Since then, they've discovered the Indian garbage patch, the South Pacific garbage patch, the North Atlantic garbage patch, and the South Atlantic garbage patch. They're all mainly waste plastic. 100 years ago, there was no plastic in the ocean. What are governments doing about this plastic in the ocean? This plastic, the garbage patches, they're all in international waters. You imagine, supposing the British government said that it was going to spend £100 million to send ships out to the Pacific to clean up the garbage patch. The British public would never agree. They would say, why the hell are you spending this money clearing up the ocean when our NHS is broke? What can countries do? There's not much they can do. Countries can just about manage to clean up their own shoreline, but they're not going to be able to fund clearing up the ocean. We can send rockets to the moon. We can send rockets to Mars. But we can't clean up our own mess that's been created in the seas of the world. This whole talk is an appeal to people who have at their disposal hundreds or thousands of millions of pounds. These are the billionaires that are in the world today. 100 years ago, there were no billionaires. I would appeal to these people, organise a fleet of ships, take them, sail it out into these ocean garbage patches and clean up the mess that the human race has created. If we look at the ocean garbage theorem, and just change the lettering, it's sending us a message. Points plus regions equals edges plus number of pieces plus three-dimensional pieces. It's telling us plastic plus rubbish equals the end of life in the ocean.